All right, welcome to exercise number 3. The meter stick is balanced, as you can see. There's nothing on either side of it. And it's right at the 50 centimeter mark. So what we're going to do is we're going to put 100 grams, 50 plus a 50 gram mass hanger, onto the left side at the 55 centimeter mark. Now, there is this, I have to do that by putting this clamp on there. The clamp also has a mass. So the first thing we've got to do is mass this set. So let's turn on my scale. We're going to put everything on here. 121.8 grams. 121.8 grams. So that's the amount of mass that's going to hang at the 5 centimeter mark. And you can find the weight by, of course, change it into kilograms, 0.1218 times 9.8 meters per second squared. Again, there's spots in your data table to do this. So now I'm going to attach this to the left-hand side. I also put the meter stick up on a brick because the mass hanger is so long it hits the table, it won't actually balance. So right at the 5 centimeter mark. And of course the meter stick falls down because there is more torque on this side. The torques are not balanced. So Newton's law, if you are in force equilibrium, if anything is in force equilibrium, the forces on the system are equal and opposite. Now when you have rotational motion, you can't just look at the forces, you have to look at the torques. So it's not just the mass, but it's where the mass is located. So to balance it out, I could put another mass on this side, but what I'm going to do is balance it out by moving more of the meter stick on the right. In other words, instead of keeping this at the center of mass, I'm going to move this off this direction until it balances. Oh, it's almost there. So let's try. Oh, look at that. Okay, so I'm going to screw it in, and it balances. So you can see that it's off the ground, and the meter stick is level. So we've got the balanced position on here. So where is it? Maybe you look like 33, but we have to look at the inner side. This is actually where we want to read from. This is the middle of the mass hanger. So it is 33. Let's actually get a little closer. So if you look at the top, you can see a little better. 1, 2, 3, 4, 5. It looks like it is 33.5 centimeters from the left end. Oops, I gotta refocus it here. And the mass is hanging at 5 centimeters. So what we want to do is measure everything relative to the fulcrum, where is the axis of rotation. So I want you to draw this. There's a little spot for you to draw it. You draw your meter stick, and where the fulcrum is, put a little like rectangle to represent the fulcrum at 33.5 centimeters. And then put a little mass hanging on there. What was the mass? It was put 121.8 grams hanging at 5 centimeters, 5.0 centimeters. Now, we're going to measure all the distances from the fulcrum. So we got to figure out how far away this mass is from the fulcrum. How do we do that? Well, the mass is at 5 centimeters. The fulcrum is at 33.5 centimeters. So to find the distance this 121 gram mass is hanging from, you take 33.5 and subtract off 5. So I think we all could do that, right? And so you have to take everything and subtract it from where the fulcrum is. Now, where was the center of mass of the meter stick? Why is it balancing? Because there's a whole bunch of meter stick over here, and it acts as if it's concentrated at the center of mass, which is at 50. What we could do is find the total weight of this side of the meter stick and figure out where the halfway point is, but that's much more complicated than it has to be. all you have to know, whenever something is moving or there's torque on something, that it acts as if all the mass were at the center of mass. So pretend that there was no meter stick, but just a mass with the weight of the meter stick hanging right here. Now remember, the mass of the meter stick is 208.7 grams. So it's like a mass was hanging here at the 50 centimeter mark, and it's how far from the fulcrum? So the weight of the mass is 2.045 newtons. That is 9.8 times 0.2087 kilograms. We figured that out in the last video, right? So we know the weight of the meter stick. Can we figure out how far it is from the fulcrum? Well, what's 50 minus 33.5? So again, on your diagram, just put a nick at 50 centimeters, and note that that's the center of mass of the meter stick. And you can put like 2.045 newtons at that point. Again, so we know the distance is 50 minus 33.5 is the distance that the meter stick is acting at, and the weight of the meter stick is 2.045. To find the torque, you multiply the weight, which is 2.045, times this distance. So again, what is 50 minus 33.5? That's 16.5, or 0.165 meters. So remember, you want everything in MKS units. So you're going to take the 2.045 newtons, multiply that by 0.165 meters, and what do you get? You get the torque that's causing the thing to go clockwise. That's negative torque. So torques that cause a system to rotate clockwise are called negative torques. Counterclockwise are positive torques. And by convention, that's how it is. It has to do with your right hand rule. If you take your right hand and your fingers point in the direction clockwise, your thumb will point backwards into the board. Now, if you want counterclockwise, that means if your fingers point counterclockwise, your thumb will point out towards you. Positive torque. So that's how the direction of torque is made. So again, so back to find the torque on the right-hand side, 2.045 times 0.165. I get a torque, the 2.045 times 0.165, 0.337. And what are the units? Newton meters. Now, even though it's a force times a distance, and that's can be energy, in this case it's a cross product, you have to keep it in Newton meters to indicate the torque. Never put joules down. Even though a Newton meter is equal to a joule, never ever write down a joule for a torque. It's just by convention. It will confuse everybody. I somehow got a little off kilter there. There we go. So now we've got this one. And again, what distance is away? Did you calculate it out by now? 0.335 centimeters minus 0.05. So it's 0.285 or 28.5 centimeters, right? So that's the distance. And what's the mass? 0.128 kilograms. And then to find the weight, we take 0.128 times 9.8. So that's 1.1936 newtons is the force on that side. So notice it's a smaller force than the weight of the meter stick. The weight of the meter stick is 2.045 newtons. So that's why this one's a little bit further away from the axis of rotation. It's a little less mass, and to balance the heavier mass, it has to be further away. So let's see how close we came. Take 0.285 times 1.1936. I get a torque of 0.340 Newton meters. So compare that with 0.337. It's very, very close. So in this exercise, we're going to get quite good values because it's easy to see where it's balanced out, and there's not an awful lot, there's no air resistance involved in this. So, there's no friction involved in this exercise. So we don't have to worry about those types of things. The only things we have to worry about is where exactly is this. We may be off by a couple millimeters, and that's pretty much where the error comes in this exercise. Okay, now on to the exercise number 4.